Rated E for engineers. Viewer discretion advised. Side effects include and are not limited to binge watching, fangirlism, and mechanics and chill.
I didn't know you guys watch hockey.
Yeah, occasionally. Mostly when we're trying to procrastinate.
Oh, really? I only started doing that after I got to BU. Wait, how does the puck travel so fast? Wouldn't the wooden stick break after so much pressure?
Well, they don't use wooden sticks anymore. They use a composite material. It allows it to flex more.
Then what does it mean to bend then?
I don't know. I don't understand it myself.
I understand. You found solace in your mechanics and materials textbook. You ignored my friendship and wisdom.
Is that from The Godfather?
You stand there and disrespect me in my field of expertise. With my friendship, you could solve anything.
What does he say next in the movie?
Be my friend. Godfather.
Okay, good. Okay, so I'll show you how it goes.
So we know from basic physics that energy equals force times displacement. We can make a similar analogy here with stress and strain to get this term known as strain energy. On this graph, strain energy, which is a form of potential energy, is the area under the curve. In this case, it's 1/2 times the stress times the strain times the differential volume. So this differential volume comes from having to account for the area and length terms in the stress and strain terms. This potential energy becomes a differential, and we have to integrate it across the entire volume to get the total energy. In the linear region, we can also use Hooke's law, where stress equals strain times elastic modulus, to further simplify this. We can substitute this stress over elastic modulus into the strain term to reduce terms. And in this case, with bending, the stress is given as this bending term, which depends on the bending moment. And then afterwards, we can separate this differential volume into a differential area times a differential length, x. So the reason for this becomes clear when we write everything out. Here we can pull the y squared and the dA into their own integral, and this integral actually ends up being the moment of inertia of the object. So we can cancel out one of the moment of inertia terms here in the bottom to get to our final result, where the strain energy for bending is the integral over the volume times the bending moment squared over 2 times the elastic modulus times the moment of inertia. So there are also other forms of this strain energy depending on how this stress is formulated. For example, if you had a stress from a normal load, or if you had a stress from torsion. So with regards to our hockey stick, we find the player's most powerful shot is the slap shot, when the player purposefully hits the ground before hitting the puck. So if we pause here and simulate the stick in Creo as a cantilevered beam, we can see that the friction force between the stick and the ground and bends the stick, generating a bending moment. Now if we look over at stress, we can see that the stress is generated along the volume of the stick. This indicates that the strain energy is being built up in the stick. Now when the stick goes back to zero displacement and hits the puck, all that stress is released from the stick, and that strain energy is transferred to the puck. So the end result is that the puck will have both the kinetic energy from the moving stick and the strain energy from the bending of the stick, and it will be able to travel faster along the ice. Woo!